it's 10 o'clock, so it's time for me to get started. Hey everyone, this is Mr. Younger. I'm here to give you an introduction to our first lab for the online lab course for PHY 241. This specifically is PHY 241, who has a lecture section of N02B, but a lab section of, if my memory serves me, as L02B. Of course, it could be L01B. I don't know, but for some reason L02B was reminding me. Not that relevant, doesn't really matter too terribly much. The main thing is we have a lab. Currently, I'm scheduling it at 10 a.m. every Thursday that I'll come on, make a video introducing you to the lab, and then you'll have until 11:59 p.m. a week from that particular Thursday to turn it in. There will occasionally be extensions, like for instance, if we didn't have lab next week, then you wouldn't be required to turn it in until 11:59 p.m. the following Thursday. But you can normally, check with me on that and just assume if we skip a week of lab, it's going to result in you getting 2 weeks to turn it in as opposed to 1 week. So just keep that in mind. Now we are actually having to do this via online, so you obviously have limited equipment that you can use. The good news is some of our labs are based on analysis of videos where we basically do curve fitting, and we use software that allows us to analyze videos and measure velocities, accelerations, and stuff like that on the actual video. So that's the way a lot of these labs will be done. We're still working on a better route of delivering labs because, as you hopefully know from all the warnings that TCC puts out, as well as the statements that I made and slowly integrating into my syllabuses, if you take an online lab, a lot of colleges and universities are not accepting that online lab for the full lab credit. The good news is the universities that we've heard that haven't taken it, they count it as some kind of elective. Some of them have 2 levels of lab that they allow you to take, and it meets for one level but not for the other. I think it's more along the lines of lab classes for science classes that are, robust and tough, but not necessarily for science majors. So they would be like the lower tier, quote unquote, lower tier labs classes, and then the students that are going to go on to become actual scientists and maybe engineers, not really sure. Those particular labs are supposed to be a little bit more rigorous, probably with a lot more detailed lab work and studying the intricacies of propagation of error, studying the intricacies of proper lab measurement, and all that good stuff. So with that being said, let me go ahead and share my screen with you so you'll know exactly what lab we're going to be doing. I'm going to go ahead and share the screen now. This should be it. So what we have here is our module for week one. Notice it says week one, January 12th to 11:59 p.m., January 18th. And this is the first module, so I normally won't have this many videos. Sometimes I do because I want you to have access to a lot of them. And I've found that, giving you a lot of different problems to look at is a way that some students really appreciate. But again, you don't have to watch a single one, to be honest with you. I'm just putting them there because these are ones that are completely relevant to what I'm teaching in that particular week, and completely helpful as further examples in case you, for instance, don't get enough examples from within the lab or from within the lecture. So they'll always be there. And then, of course, you have the homework links, which links you to the homework assignments. Now, these are the dates, and actually, I believe these dates are correct, but these are the dates that you see on Canvas that are are a result of the Pearson MyLab and Mastering assignments. As I warned you, though, in this case, even though these dates seem to be correct, actually, that one does not seem to be correct. This one's not correct. So that's a good lesson to you. Is I pointed out, never, ever, 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 ever trust the due dates with any MyLab and Mastering assignments when looking at the due dates on Canvas. Don't trust that at all. This is the actual due date for Chapter 1 Conceptual, and it's also the same due date as Chapter 1 Homework. This is not the due date for physics primer. This is the due date for Introduction to Mastering Physics, and it's the same due date as physics primer has. But as you can see, clearly Canvas wrote them, put down dates that were not what I meant. So I'm not really sure what's going on with that. You do have to, and this date is wrong here as well, but that's not supposed to be wrong. Let me fix that while I'm here. I've actually changed this in your syllabus. You are actually supposed to have this uh, syllabus quote filled out and turned in. I think the date was by January 26th. Yes, it's January 26th is when that's supposed to be in. So now I'm changing that date right as you watch me. So now you can see that the syllabus copy and paste assignment is in fact a assignment that's due on the 26th of January. And let's see. Now, beyond the homeworks, you then run into lab accoutrements, and that's what we're going to be talking about. I want you to understand that we I actually put out the lab document, which is what this is right here, Introduction to Lab, and then I make an assignment, which is what this is right here, Intro to Lab, and then that assignment inside tells you all the stuff that I warned you about in your syllabus about how to do the lab. But in addition to that, this is where you turn it in. So it'll be turned in here. The due date, of course, is a week from today. Now, if I find out that we don't have a lab next week, and I'm pretty confident we don't because of Martin Luther King Day, I believe it's coming up Martin Luther King Day, then this will be due on January 22nd if we're on next week. But if we don't have lab next week, and you have to check the syllabus for that, it'll be due January 29th. But I'm putting this right here for right now. It's probably easy enough where you can definitely get it done today, much less by that time. But either way, I just want to make sure you knew that. So the other thing I wanted to point out about this lab section in week one module is, again, it says lab accoutrements. This is further explanation of something that's written in the lab. This is further explanation of something that's written in the lab. Later labs will actually teach you to read vernier calipers, even though in your cases you're not going to have vernier calipers at your home with you. It's still a skill that you should know, and this teaches you how to do that. As I said, this is the lab write-up, and that's what I do with my face-to-face labs. I put out a lab write-up in Word form so that you can type the actual data directly into the Word document. Of course, I require everybody that puts anything into the lab document, if they actually type it, it has to be in a font other than black. So make sure you do that. That includes the fact that on the very first page, which could be a title page, but doesn't necessarily have to be a title page, but on the very first page, you need your name, the name of the person that's turning in the lab, and then if you had anybody that you were working with in the lab, which might not happen in this class since this is an online lab. But if you did, then you need to mark partners and then put the name of each partner next to the name partner so that I can clearly see, oh, this person is the person turning it in and these people are their partners. That technically should be in a font other than black as well. That being said, I usually don't take off if you forget to make the names in black font, I mean in font other than black. But I do take off for everything else that's actually been typed into the document and is not a color of font other than black. Some students choose to actually highlight the things that they type in. They'll leave the actual letters that they type in black, but they'll do like a yellow highlight over the numbers that they entered. That's acceptable as well. I do not mind that. The big thing is I want to be able to quickly open up that document, which I keep saying Word is what you're filling it in, but you're ultimately going to turn it as a PDF. But I want to be able to open up your PDF document, immediately find out who the student is, who the partners are, and then I want to also immediately find out everything they entered in the in the lab document easily. So I don't want to have to figure out, is this something they typed in or is this something that the original lab report had in it? That's why I'm asking you to use a font other than black. Uh, any any calculations or every type of calculation you do in a given lab, you're supposed to have exactly one sample calc shown of each of those types of calculations. So that means, for instance, if in a lab you are required to make a measurement of the length of a block. You would take like 5 or 6 measurements of that, or 10 measurements, or whatever. It's normally like 5 measurements. You take 5 measurements of that. Then the best estimate of what that measurement should be will be the average of those 5 measurements. And to be honest with you, though, we're never going to do this in our lab. To be honest with you, the actual best estimate of data is not the average, but the weighted average, where you actually give more weight to the measurements that were had less error. So if you imagine you were like a manager of 20 labs across the country or something like that, you might find out that one lab is all made of, PhDs that have worked on experimental science for decades, and therefore they get very low error results, and you have a sense of exactly what those errors are. And then you have other labs that are, made of people right out of high school, or in some cases, kids right in high school. You might suspect their lab, or excuse me, their lab data might have higher error. So if that's the case, then you could do a weighted average by taking and multiplying the result that each particular lab had by 1 over their lab's error, maybe squared. That's normally what I do, is the lab error squared. So you're literally going to take one lab results and divide it by the square of their average error, and then you're going to take another lab's result and divide it by the square of their average error, and you're going to do that for all the different labs. And then you're going to divide all that by the sum of the squares of the reciprocals of those errors. So, in other words, the things that you ended up multiplying by your individual lab results, each of those are squared reciprocals of their error. So you want to take and add all those up, and that sort of normalizes it, make sure it has the right units and all that good stuff. So that really is the better version of the best estimate of any data taken. Again, that is your weighted average as opposed to your regular average. That being said, as I mentioned, we rarely, if ever, get to do weighted averages in our physics lab. The only time we really use them in physics is to calculate grades. Okay, so you need to know how to calculate weighted averages so that you can understand how your GPA works or how your course grades work. But anyways, that's the idea behind taking multiple measurements. The big idea, of course, is that when you take multiple measurements, you actually remove random error, but you can't remove systematic error by statistics like that. So it just has to be to address the random error. And random error is like, sometimes you look at the vernier caliper from leaning from this side and you read the number too big. Sometimes you look at it from this side and you read the number too small. That, in principle, is supposed to be something you work out so you never have that type of an error, but that is a potential random error, because if you're looking from one side, it's an error that makes it bigger. If you're looking from another side, it's an error that makes the number smaller. And obviously, if you do that in equal amounts over a large number of trials, then the net effect would be zero if you actually did take multiple trials. So that's what that's about. As I said, this is where, once you're finished with the lab report, which requires you, like I said, to do one calculation of each type. So for instance, I was telling you about calculating an average. When you actually calculate an average, let's say, of the length of a rectangular block, well, later in the lab, you're going to have to calculate the average of the width of the block. And later in the lab, you're going to have to calculate an average of the height of the block. Well, you also might later have to measure repeatedly the mass of an object 3 or 4 times and take its average. In those cases, if you did one sample calculation with an error, I mean, with the calculating an average in the first trial, then you don't have to do any more averages, even though they're averages of other quantities. So you need one sample calculation of the variety of an average, and no more, even if it's measuring a different quantity. The other things you got to put in your lab report is any graphs that you're required to make. I want to see those, even if the lab explicitly says you don't need to print it. And by the way, we never print in my lab. That's why I'm doing everything electronically. But even if it doesn't say you have to print it, I still want you to turn in that lab. If it explicitly says you do not need to and you put it in, I might actually give you a little extra credit for that. Okay. Now, what you're going to do is, as I said, fill in that Word document with any typeset stuff that you fill in has to be in a font color other than black. And every sample calculation, not only do you need to put it in there, you need to put it in there exactly where it asks for it. Or in some cases, because I'm asking for more sample calcs than necessarily the lab reports do, then I want the sample calculation put right where that section of the analysis of the data is done, or where they instruct you to calculate that calculation. Okay. In other words, I don't want all your calculations or all your graphs or all your data to be at the very end of the lab report. I want it right there where you're requested to do it, or right there where you know to do it, or whatever. Additionally, uh, uh, I want to make sure that you guys know that you should fill in any answers to any questions. So if you ever in a lab report see a question mark, read it, make sure it's not a rhetorical question, and it never is really. I can't remember a single rhetorical question we asked in here. But the main thing is when you find a question mark in your lab report, you want to put a cursor right to the right of that question mark, and you want to hit return, return, return. That gives you basically three spaces, and then sandwiched in the middle of that space, so you have a little white space above and a little white space below. I want you to type in the answer to that question. Okay. Again, with a font color other than black, you're going to type in that specific issue or thing. Or excuse me, that answer to the question. Sorry, couldn't think of the word answer. So yeah, that's what's going to happen. You're going to type in the answer to that question right there, and you should answer all the questions. Okay. If it's a multiple choice type question, then you need to unambiguously mark just the correct answer. If I see marks on multiple answers, then if there's a mark on every one and one's not marked, I'm going to count the not marked one as the answer you chose. But if you've got multiple ones marked, I'm going to assume that you didn't actually answer it, and you're going to lose points for that. So make sure you do answer all those questions. Make sure you do all the sample calculations, as I told you, one of every type. Uh, and the way you do them is you can do them by hand. You can typeset them in Microsoft Word, but I don't want you wasting time to do that. That takes a lot of time. If you just want to do it because you like doing it, then by all means. But I would say, keep a check on your OCD, if you will, and don't allow yourself to be a slave to making things nice and pretty when they don't have to be so nice or so pretty and can save you a lot of time. So what I recommend normally people do for their sample calculations is they write them out very neatly on a sheet of paper, and then they take a photograph of a single calculation, and then they insert that photograph into the Word document again, right where you had to do that calculation. Same thing with the graphs, same things with the data. If you make a data table in Excel or whatever, you can put the data in there, and if you make a graph with Excel or whatever, you can take a photograph of that and paste that into the Word document. Again, I want those that data and that graph to be exactly where they told you to make it, or exactly where in the analysis you had to make it. So there could be some ambiguity from one lab to the next. Like one person might put the lab where the procedure said for you to do it, and another person might put the I said lab. One person might put the graph or the data or the sample calc right where the procedure said to do it. Another person might put it where the analysis suggested, and they're both going to be counted right. The main thing is I don't want them at random spots, and I don't want them all at the end. Okay. So once you have this Word document completely filled in with non-black font, filled in with all the sample calculations, filled in with all the graphs and all the data that I've suggested you're supposed to be putting in it, once all and answers to all the questions, once you've done all that, you should then save the Word document as some title, as some file name that includes the lab, so intro to lab, but also includes like your initials or something. So I'm Billy Younger, so you might want to say BY underscore intro to lab, and that would be the name of the Word file. Then once you've checked it, make sure it all looks good and it's very neat, and none of the pictures that are data or graphs that you've inserted are so small that an old person like me can't read the text. If they are too small, that's going to lose you points. So you'll make sure you make it big enough. I'd rather you, because we're not printing it out, I'd rather you waste, quote unquote, a lot of paper by making these things bigger than by saving paper by making them so small that I can't read. So make sure you make them big enough. But again, once all that's done in the Word document and you saved it with your initials and the lab name, then you want to save it again. But this time you're going to save it as a PDF. And the way you do that in the Microsoft Word window, down at the bottom, it'll say Microsoft DocX or something like that right below the menu where you find your files and stuff. If you click on that, it's called a radio button. It'll show you all the different formats that Word lets you save them in, and the format that you want to save it in is PDF. If you have your own copy of Microsoft Word, you might not have access to that. So you want to make sure you get your free, quote unquote, free access to the Microsoft Office suite that you're allowed as a student of TCC. If you don't recall how to do that, you can contact TCC Help by email. That's usually the best way, but you can also call them at 757-822-1122. So that's another way you can contact them. But the main thing is you do have to save it as a PDF, and all of the assignments that you turn into me, which doesn't include, of course, mastering because you don't actually turn anything in there. You just do it on the website, and it shows up in my grade book as well as the my lab and mastering grade book. I've got my course, what they call fully integrated, so you should never be going to my lab and mastering except through Canvas. And by doing that, it not only allows you to do the homework as if you never left Canvas, it also imports the grade into my Canvas gradebook. So make sure you get that done. So other than the MyLab and mastering, all the assignments that you have to turn in, quote unquote, turn in, are going to be turned in as PDF documents. That includes all the extra credits and all that good stuff. Uh, Down here, you'll see intro to lab comments. When you see something like that that says comments, that's me providing it ahead of time because if you open that text document up, you'll see the common uh, errors that people made in the past on that particular lab report, and I give that to you so you can avoid making those same errors because each one of those errors cost you at least 5 points because I take everything off in increments of five, and by catching what I meant in these comments, you might prevent yourself from making the same mistake so your lab grade will be better. So that's why the comments.text are in there. For this class, we're doing the labs online, and the way we make a lab that was meant to be in class into an online lab is we have these things right here, which have the title of the lab in it, but then say addendum because it's an addition we've made to the actual lab that now allows you to conduct the lab at home. So you're going to need to look at that. In this particular lab, you're also going to have to measure the periods of oscillation for some springs, and therefore I've included these videos right here of periods of springs with masses on them vibrating up and down so that you can actually see a video and then time it yourself using a stopwatch on your cell phone or something like that. Additionally, you'll see down here the extra credit, and that's where you turn in those extra credit assignments. Those, of course, are normally handwritten, photographed, then saved as a PDF, and then turned in. Now, let's go to this particular lab. I'm sorry this one's taking longer than normal because I got to run you through the whole rigmarole so you understand exactly how the labs are done. But I'm going to go ahead and open up the Intro to Lab document, which is the Word document that you guys will download to do the lab. I'm going to make it bigger so everybody can see it on the screen. Intro to Lab, perform several measurements which require significant figures for an understanding of the results obtained. In particular, estimates will be obtained for pi and technically for half g. It says g, but it's actually for 1/2 g. The magnitude of the acceleration of a falling mass near Earth's surface and for the period of an oscillating spring. Sorry about that. The apparatus needed, obviously, some of these things are things that you would have in the lab, but you can't have here. You probably don't have, for instance, a meter stick at home. Hopefully you do. That would be great. If you don't, but that's okay though. Uh, Meter stick holder, you're not going to have that. You might have a excuse me, you might have a golf ball. Hopefully, you have some kind of ball that you could use, measuring tape, so on and so forth. Now, it starts off with definitions and conventions. So, this lab is introducing you to the typical things that we do in a lab in freshman slash sophomore level science classes. Uh, we mostly use sig fig and sig fig rules to keep us from overestimating or underestimating the precision of our experiments. So, I give you different from this one, different from this explanation. I give you a very specific set of significant digit rules that teach you exactly how a number is understood to have whatever number of sig figs it has. In other words, I give you a specific way that's unambiguous that tells you definitively exactly how many sig figs a number has. Now, it is in one of those documents that I pointed out to you that can help you learn how to do this stuff, but I'm going to explain it in words right now. So the first rule in trying to determine how many sig figs are significant figures are significant digits, those are all different words for the same thing. The definitive rule that I use for determining the number of sig figs is one, the leftmost non-zero digit in any number is what we call the most significant digit, which I abbreviate by MSD. Okay. So, for instance, the number 1500, that's 1500, the 1 is the most significant digit. And the number 0.00150, the 1 there is also the most significant digit. In the number 100 or excuse me, the number 15.0, the 1 again is the most significant digit. Now, the second rule. First rule was the leftmost non-zero digit is the most significant digit, and obviously, since it's called the most significant digit, that means it's also a sig fig. The second rule is if there is no decimal present, then the rightmost non-zero digit is the least significant digit, or LSD as we abbreviate it. So in the number 1500, since there's no decimal present, because I literally read it as 1500, in that case, the 5 is the least significant digit. So in the number 1500, according to the rule, that has no decimal present. And when no decimal is present, it's the rightmost non-zero digit that is the least significant digit. So in 1500, that's the 5. So in the number 1500, the 1 is the most significant digit, the 5 is the least significant digit, and the two zeros are just placeholders. I can't do the 15.0 or the 0.00150 because both of those have decimals in it. So that brings me to the third rule. The second rule, of course, being that if there's no decimal present, the rightmost non-zero digit is the least significant digit. The third rule is if there is a decimal present, then the rightmost digit, period. The rightmost digit is the least significant digit. So in the number 1500, this one doesn't apply because the number 1500 has no decimal present. If, on the other hand, I did write 1500 dot, then that's me taking the pain in the butt time to put a decimal there, and it would almost always be misunderstood. So the way I would normally do that is I'd write 1500 decimal, and then I'd write a 0 to the right of the decimal, and I'd underline it because that underline is a way that I tell my students, and hopefully my students tell me that, hey, I've included this digit for future calculations, but it's not a significant digit. Okay. So again, this third rule is if there is a decimal present, the rightmost digit is the least significant. So in the number 15.0, the 0 is the least significant digit. In the number 0.00150, the 0 to the right of the 5 is the least significant digit. So what you see is from these three rules, we found that 1500 has two sig figs. We found that 1500 decimal point has four sig figs. We found that 1500 decimal point 0 with a line under it has four sig figs. We found that 15.0 has three sig figs, and we found that 0.00150 has three sig figs. Okay, so that's the unambiguous rule that I established for my lab for sig figs. Okay, that's just for determining the number of sig figs. Now, your textbook and therefore the practice test questions that you're going to run into and potentially the questions that you could get on your actual face-to-face tests and online tests, they ask you the number 1500 with no decimal point. How many sig figs does that have? The author, because he's using a different sig fig rule than I do, the author is saying that that number is ambiguous. Okay, and that's the answer we expect on actual test questions. So if the test question has a multiple choice and it's 1500 with no decimal, or 5,000 with no decimal, or 12 million with no decimal, all of those numbers have a butt ton of zeros and a non-zero digit or two, and all of those numbers are ambiguous according to the author. So just keep that in mind when you're doing your tests. Now, in addition to being able to count the number of sig figs a number has, you also need to understand how do you deal with those significant figures when you add two numbers that have been measured. So the fundamental idea within the science lab is that anytime you make a measurement, that measurement has to have an uncertainty or an error in it. Now, generally speaking, we assume if we just see a number that someone reported like 15.0, we assume that the uncertainty there has to be at least zero point 0.1 because we took the time to write the zero in the tens place and it's not underlined. So that means it's a sig fig, and that means that's the least significant digit, and that least significant digit is in the tenths place. And we assume a plus or minus one in that place as the error. Now, if you actually believe it's more, then you should take the time to write 15.0 plus or minus 0.2 or plus or minus zero point 0.3 or plus or minus zero point 0.4. But the main thing is the digit of uncertainty has to be in the exact same number column as the least significant digit. You can't go beyond it because obviously if you know 15.0 to plus or minus 1 or zero point 0.1 or plus or minus zero point 0.2 or plus or minus zero point 0.3, then you know there's some error in the tenths place, and therefore there's no chance in heck that you know what the digit is in the hundredths place or the thousandths place, and so on and so forth. So that's a key rule that's going to stick even when we're not doing it. This error propagation with sig figs. The error or the uncertainty in a measurement is always, as a bare minimum, plus or minus one in the number place where the least significant digit is. It can be higher, but it's your responsibility to indicate that if it is higher. So keep that in mind. That's something else. Now, when you take those two numbers that are measured and therefore have uncertainty, what if you have to do mathematical operations on them? What if you have to add those two numbers or subtract those two numbers? What then is the uncertainty of the resulting sum or difference that you got? Sorry, I decided at the last minute to use the name of the answer for an addition and subtraction problem, so that's why I had that weird little and sum. But anyways, when you do add or subtract numbers with errors, what you're supposed to do is locate the precision of each of the numbers that you're adding or subtracting. The precision means what is the least significant digit, in what number place is that least significant digit. Like 15.0 is to a precision of 1/10. The number 1500, according to my sig fig rules, is uncertain in the hundreds place because 1500, the 5 is the least significant digit, and that's in the hundreds place. The rightmost zero is in the one place. The or the second from the right zero is in the tens place, and then the 5 is in the hundreds place. So the precision of 1500 is the hundreds, not hundredths. The difference is the hundredths is the second decimal place, whereas the hundreds is the second over from the ones place or from the decimal. It's actually the second over from the ones from the decimal, not from the ones place. It's to the left of the ones place. So when you add or subtract numbers, you look at all the precisions of all the numbers you're adding and subtracting, and the number with the least precision is gives you the precision of the result. So if you added 15.00000008, you know, all of those digits are significant. The one, the five, all the zeros, and the eight, or even if you didn't have the eight at the one at the end, the one, the five, and all the zeros after the decimal, those are all very high precision numbers, and all those digits after the decimal are in fact levels of precision that are way, way, way more precise than the 1500. But still, if all your numbers were all like that, but you added it to 1500, you have to round the addition answer to the hundreds place, no matter what. So that's with adding or subtracting. Notice you don't actually use sig figs when you're adding or subtracting numbers to get the new sum or difference. If you're multiplying or dividing, you do go back to using sig figs. And the rule is that when you multiply or divide any number of numbers, you look at all the numbers that you're multiplying or dividing or both, and you find which one has the least number of sig figs. Then your answer to the multiplication or the division problem is to be rounded to that many sig figs. So if you're, multiplying numbers that have 3 sig figs, 7 sig figs, 12 sig figs, 9 sig figs, the 3 sig fig is the least significant figures, so your answer is going to have to be rounded to 3 sig figs. Now, that turns out all these significant digit rules are a good first order approximation to how errors, quote unquote, propagate when you take measured quantities and put them in formulas, but it's not completely correct. That's why I've had that one video that says when sig figs lead you to errors. So definitely watch that and you'll get understanding why we actually use the more robust propagation of error formulas that I'll teach you later. But right now, we're just going to do all the labs, unless I explicitly tell you otherwise, we're going to do all the labs using sig figs. Okay? There will be labs later where you're going to use specifically propagation of error formulas like you're supposed to. That's really what scientists have to do when they're doing actual research, as opposed to sig fig stuff. But like I said, a sig fig is a perfectly acceptable first order approximation to proper digit analysis. Now, I've told you about adding and subtracting. The only thing that's left with regards to sig figs is what if I take the logarithm of a number that's been measured, or what if I take the sine or the inverse tangent or the cosine of a number? In that case, what we use is if you put in 1, 2, or 3 sig figs, then you produce an answer that has exactly that same number of sig figs. Some of those functions that you might use might actually take more than one quantity, and when that happens, you take the number of sig figs that the one that had the least number of sig figs had, and use that to round your answer to that least number of sig figs. So if, for instance, I take the sine of 15.0, I should report that to 3 sig figs because 15.0 has 3 sig figs. If I took the sine of 1500, I should report that answer to 2 sig figs. Now, one other rule regarding this, and it's very important that you pay attention to this part. If you do actually round these numbers and then you have to use that number later for a calculation, it's very important that you keep at least one extra digit. So when you're first writing down and rounding the result of an operation with numbers that were measured, you should go ahead and make a note each time you do a calculation of where the least significant digit is, and then keep one digit past that, or 2 digits past that, or some number of digits, 1 or greater, past that, and just underline them, because that way you won't repeatedly round. Because if you repeatedly round, you'll get a number that bears no resemblance to what we expect as the right answer. So when you do like a measurement of distance and you get it to maybe one decimal place, and then you do a measurement of time and you get that to maybe two decimal places. Then you divide the distance by the time, that gives you the velocity. What I'm saying here is when you do that, you've got to use the proper sig fig rules to round that velocity. But if you're now going to use that velocity sometime later for another calculation, then you don't want to just take that rounded value. You want to take that rounded or that value before it's rounded and add one extra digit and just underline it so you can track where the least significant digit is. So you should always do that in your homeworks and your labs and everything. So always keep it at least one extra digit beyond the sig figs until the very end. And then when you report them to the appropriate number of sig figs. If you want to report them with more, that's fine. Just in my lab, you need to underline any digits that aren't significant figures. Then I won't take off for you giving me too many digits or giving me too few digits or whatever. Uh, Here's where the book talks about the best estimate. Again, I told you that the best estimate is a weighted average, but we're never going to do that in here. So to date, whenever you take a average of several trials, then the average is your best estimate of what that measurement should be. I would say it's never acceptable to do less than five measurements. And to be honest with you, five is a joke from a statistical standpoint. Even 25 is a joke from a statistical standpoint. Of course, the more trials you get, the closer you're coming to being statistically good, but really it needs an infinite number of digits to be completely statistically helpful. Well, I shouldn't say completely, but anyways, you can actually, there's ways you can calculate statistically how many digits you need if you want a certain precision, so on and so forth. But the main thing is the more trials you have, the more representative the statistics is. Okay. Now, if you happen to be measuring two quantities, one and neither of which are quantities that you can look up as tabulated. So, for instance, I mean things that are able to be looked up are like the acceleration due to gravity on average for planet Earth, or the acceleration due to gravity at a specific location on Earth. Those are things you can actually readily look up. Also, the gravitational constant in Newton's law of gravity, that's a thing that you could look up. Planck's constant's the thing you could look up. The mass of an electron, the mass of a proton, the charge of an electron, the charge of a proton. All those are things you can look up. But, for instance, there is also a concept called conservation of momentum. There's also a concept called conservation of energy. So some labs might involve you testing those concepts of conservation of momentum or conservation of energy. In that case, you might be called upon to push a little car and then measure its velocity and take its mass and multiply the mass times the velocity to get its momentum. And then it's going to collide with something. And then after that collision, it's going to have a new momentum, as will the thing that you collided with. And one of the things we do in lab is test conservation of momentum. So we would calculate the total momentum of you pushing that car and maybe pushing another car before the collision. And then we calculate the momentum after the collision of both of those things. And you can't look that up. There's never going to be like a book of the random students pushing of a car at a random date at a random lab in a random college or whatever, right? So when you're comparing two numbers like that are supposed to be equal according to the theory you're testing, but cannot be tabulated, then what we use is something called the percent difference, and that's what you see here. What you want to do then is you want to take the difference between the two values that are supposed to be equal and put them in absolute value bars, or more easily just take the bigger one and subtract from it the smaller one, and that'll be your absolute difference between the two quantities. Now, you want to know how big that is relative to the quantity. That's why you divide it by quote unquote something, right? In this case, you're going to divide it by the average of the two quantities, because the two quantities, neither one is, got a lock on what the right one is. Both of them could be equally wrong. So the best estimate of them is the average of the two. So you end up dividing the absolute difference by the average of the two. That gives you a decimal. And then you move the decimal two places to the right, either by just physically moving it or multiplying by 100, like this page says. So that's the percent difference. If, on the other hand, you're doing a lab to determine, for instance, gravitational acceleration, then you can use the percent error. And that's what this formula right here is. Notice they have a very specific order. It's measured minus accepted. I never remembered whether it's accepted minus measured or measured minus accepted. So I always treat it like I do the absolute difference above. I usually take the big number minus the small number, and I never report negatives. But there's a large fraction of scientists in the universe that want to know specifically whether your percent error is positive or negative, because that tells them very specifically if everybody in the world is sticking to measured minus accepted and it comes out to be a positive one, that means you measured a value that was larger than what it was supposed to be. If you get a negative percent error, that means you measured a value that was smaller than it was supposed to be. And that's an important thing to understand from a scientist standpoint. So, the reason why I'm telling you this is the technical formula should be measured minus accepted, but I'm okay with you always turning in a positive value. That's certainly fine. I'm not going to take off points for it. Okay. Not only that, technically you should be using, in some sense, significant digit rules, but when percent errors come along, and percent differences, I usually tell everybody to use exactly one sig fig on the percent error, but I usually have the caveat that if it's 1% and the second digit is like a 3 or 4, then guess what? That second digit is 30% of the first, so it's probably better that you go ahead and include two sig figs on that percent difference or percent error, or later just the uncertainty measurement that we're going to be using. So be advised, error measurement should be to one sig fig, unless they're 1.3 or higher with 1 as the leading number, then you should probably use two sig figs. That being said, I'm never going to take off for you only using 1 or for you only using 2. I'm not going to take off for that. I'm just trying to give you good experimental technique. Uh, so there's our percent errors. Now, here's what the lab is requiring us to do. You're going to take 5 different cylindrical objects, like this coffee cup, which isn't technically cylindrical because it gets smaller here, but the main thing you're using it for is the round top, because the round top means that it should have a circumference given by pi times the diameter. So what you're supposed to do is take 5 cylindrical objects from your house and measure the circumference around them with a tape measure. Now, what you can do if you don't have an actual cloth tape, by the way, if you try to use a regular tape measure, they're not made to bend as easily as you want to go around a round thing. They're actually made of metal and it's beveled like this so that they stay stiff on their own. If you go bending them around it, you could very well ruin the tape measure. So don't do that. And by tape measure that I'm talking about here is like this kind of guy. I knew I had one laying here. So this thing has a groove set up on it so that it actually keeps it stiff even though I extend it. You wouldn't want to use that. But what you can use is just the edge of a piece of paper. You can wrap it already around and then make a little mark where they overlap, and then just take out a ruler and measure that actual circumference by going from the end to the pencil mark. Okay, that's how you can determine the circumference. Then you're going to take that same ruler or whatever you're using for your measurement and measure the diameter, and that's the largest distance across the circular thing. Now, since circumference is equal to pi times diameter, you can just divide the circumference by the diameter as long as you're using the same units, which in physics we're supposed to be using the SI, so you should be using centimeters or meters or millimeters. But as long as you use the same unit for the circumference and the diameter, then all you have to do is divide the circumference by the diameter, and that will give you pi. Pi is supposed to be 3.14159. I doubt you're going to be able to get more than 3 sig figs in these measurements. And if you're measuring with a meter stick, by the way, you should, a meter stick or a picture of a meter stick, which you're going to find out is what you're going to be using unless you have your own. But when you're measuring with a regular meter stick, that's marked to the nearest millimeter, and you're supposed to be able to estimate one digit beyond the finest markings on a ruler. So that means all of your measurements with a meter stick or anything graduated like a meter stick should have 2 decimal places if you're measuring it in centimeters. Okay, if you're measuring in millimeters, it's only going to have one decimal place, but the point is that's still the same thing. So you're going to have two decimal places in any number you make with something like a meter stick if you're measuring that in centimeters. The only time that's not true is when you've got some technical difficulty with making the measurement. So, for instance, if you're measuring something that's supposed to be a rectangle, like say this GoPro camera here, you can see this edge is actually rounded instead of coming to a sharp point. So you're going to lay a device next to it to measure it, and you're going to have to estimate exactly where this edge is because that top edge isn't actually touching the straight edge of the ruler device. So that kind of consideration by itself might compel you to say, hey, I think the error is so bad that I can't really truly estimate that second decimal place in centimeters. And then, if that is truly the case, now this one actually had such a small radius of curvature, it probably wouldn't present a problem. But in other cases, it can. But in that case, then you need to not only use one decimal place, you need to write out why so that I don't take off points for using less. Other things could be you're trying to measure something rectangular, but the end is not straight. Okay, if the end's not straight, then you're sort of arguing that the thing's a rectangle when it's really not a rectangle. So in that case, you'd measure the length at one location, another location, another location, another location, all along that curvy rectangular end, and the average of those gives, in some sense, a really average measurement of that length. If that back and forth is so large that it varies markedly in that second decimal place. Like in one case, that second decimal place is a 7, in another part it's a 2. Then guess what? It's probably not useful to use that second decimal place. So those are the reasons why you wouldn't necessarily measure to two decimal places in the centimeter scale, even though you're using a measuring device that looks like and is graduated like a meter stick. Okay. Other than that, you should always have two decimal places when you measure it in centimeters. Now, you're going to do this with five different objects. You're going to get five different, well, technically, you'll get five different measurements of circumference, different measurements of diameter for each individual object. Then you're going to take the average circumference and the average diameter, and your book might tell you three. That's acceptable as well. Usually I stick to five, and if it tells you three and you do five, I'm probably going to give you a little extra credit. You just need to make a note of it and say, hey, it told me I only had to do three, but I did five. So write that in your lab report as well. Again, if you type that, you don't want it to be in black font. But when you do this, when you actually take the five measurements of circumference, then you're going to take an average of that. When you take the five measurements of diameter, you're going to take an average of that. Then you're going to take that average, which is the best estimate of the circumference, and divide it by the best estimate of the diameter. And that's going to give you your best estimate for that particular value of pi for that particular cylindrical object. Now you're going to repeat the same thing for four others. When all that's done, your best estimate of pi is the average of those five measurements that you got for pi. It would be helpful, and this lab is written this way, if all the lab students got together and turned in their values of pi, then we could take the average of the averages and probably get a slightly better result. In reality, it might turn out that one or two lab groups got better values of pi than the class did. And that's okay too. But just remember, the more measurements you make and the more skilled the people making the measurements are, the more likely you are to get a good value of pi. Now, since you're probably not going to have more than three sig figs in most cases, you're probably only going to have pi to three sig figs to compare it to, and there's no reason to take 3.14159 and compare that to 3.18 or something. No, if you only have three sig figs, go ahead and compare it to what pi is to three sig figs, which would be 3.14. Now, the next part is finding G. And again, as I told you, you're actually finding 1/2 G. But what you're going to do is you're going to measure up like a wall. Or this is what we do in our class. We actually had a 2 meter marking in our door frames, and we marked it with tape. And then you take this golf ball and line up the bottom of the golf ball with the bottom edge of the tape, and the bottom edge of the tape is to two decimal places in centimeters, 200 centimeters up. In other words, 2 meters, but it's 200.00 centimeters up. And what you're going to do is drop that, and then it's going to hit the ground, and someone else in your lab group normally would be the one measuring with a stopwatch how long it takes. So in this case, you might actually need someone to help you if you're doing this measurement. One person to start the timer and stop the timer, and another person to drop the ball. What I have discovered over time is it's probably better for you to watch when the ball is released and start the timer yourself, and then wait for the sound of the ball hitting without watching it. Don't watch the ball fall all the way down because you're liable to hit it a little earlier. Just sort of jumping the gun. So I found it better to watch it be released, hit the stopwatch, and then listen for it hitting and hit the stopwatch a second time. Now, your reflex time is a marked fraction of the time required for that ball to fall 2 meters. So we really have a big problem here. And the way we've dealt with this in this lab is we tell you that only accept values of the time of fall between 0.60 seconds and 0.70 seconds. So if you get a number that's 0.59, you don't record that. If you get a number that's 0.58, you don't record that. If you get a number that's 7.1, you don't, or 0.71, you don't record that. If you get a number that's 0.78, you don't record that. If you get 0.60, 0.61, 0.62, 0.63, dot, 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 on up to 0.70, then you do record it. And the lab manual wants you to do 5 of those measurements. Okay. The other part was you're going to take two little beat up masses is what you're supposed to take in class. They're two 100-gram masses, and they beat up and they look like crap. And I remember when I took a lab like this for the first time, I remembered seeing these weights. I'm like, these can't be that good. Why are we using this? Well, this lab and this particular part of the lab shows you why it really doesn't matter. Uh, they're going to be very, very close to one another, which is what's relevant. Are you able to repeat the measurement over and over again? That's indicated by how well two random 100-gram masses compares to two other random 100-gram masses. So in principle, what you do is take 200-gram masses to carry them over to the electronic balance, measure them in grams to probably to one decimal place, maybe even to two decimal places, then take two other random 100-gram masses and put them on electronic balance and weigh that to one or two decimal places. And then what you're going to compare is those two values by using a percent difference. And you're going to find that percent difference is markedly smaller even than 1%. And what we're shooting for in these labs is to get, less than 10% error, preferably less than 5% error. Getting less than 1% error is awesome, and we hope you can get that every time, but we realize that the limitations of our lab are probably going to keep us in the 5% range at most. All right. So that's what you're doing with this lab. And again, the addendum tells you how to do that. You can see here's the best estimate for pi. Since you guys are not working in a group, you might not have any of these filled out. That's fine. If you guys want to communicate with each other and share, then that would be great. Y'all can just, exchange emails or whatever. But the main thing is you want your 5 values right here. The best estimate would be your average. You're going to put it here. If you actually had the groups, then the best average would be the average of this and all these and all these. Your percent error is where you're gonna put that right there. And this is the case for pi, not for the masses. Notice we've went on to the pi values. We're no longer talking about the masses. So you're going to put these pi values. I might have misread that initially because I might have thought this was still the table for that other one. So if my words say that, I apologize. I'm now correcting it. These are your pi values that you got. These are the ones that your class got. This is your best estimate. Like I said, if you didn't use your class, you're going to take the average of that. This is the percent error between 3.14 and it, assuming you had 3 sig figs, and this is where you show the work. What work are you going to show? Well, it doesn't necessarily say, but you calculated an average So I need to see an average. You know, you calculated h over t squared. So I need to see an average. I know I need to see a calculation of h over t squared for that part of the lab, so on and so forth. But for the pi part, what we need is an average and dividing circumference by diameter. That's the two sample calculations. And since you did the average calculation here, you don't need to show any other average calculations for the rest of the lab. The later next lab you have to do another one, and the lab after that you have to do another one, but you only have to do one per lab report. All right, so there's where your pi analysis works out. Here's where your analysis of 1/2 g works out. So what we're supposed to do right here is the distance of fall is supposed to be 200.00 centimeters, or 2.0000 meters is what's supposed to go here, assuming you can measure it that precisely. If you can't, then it might be 200.0 centimeters, or 200 decimal point centimeters, or 2.00 centimeters, or 2.000 or excuse me 2.00 meters, or 2.000 meters. Either of those are acceptable. You're ultimately going to have to use the meter version to get the right value of g, though. Okay. Now the time of fall, these are the ones where you're going to fill in only the values between zero point 0.6 inclusively and zero point 0.7 inclusively. So 0.60 and 0.70 are acceptable, but so are 0.61, 0.69, 0.62, 0.68, 0.63, 0.67. All those values are okay, and you'll have 5 of them. Now what you're going to do is take that 2 meters and divide it by the square of this time and put it right here. Take that 2 meters, divide it by the square of this time and put it there. You actually physically might need to go ahead and calculate the square first, because if you type in 2.00 divided by 0.65 squared, if you don't use parentheses, it's going to square the whole it's going to square just the last version of the 2.5 and might not give you the number you expect. So be careful with that. What I normally do is write 2.00 divided by left parentheses 0.65 squared, right parentheses, and then hit equals. But that's how you're going to fill out each of these little rows, is by doing the 2 divided by the square of the time and put it right here. That should come out in meters per second every second, which notice it's indicated here as it's indicated here as it's indicated here. Because of these parenthetical units, you don't have to actually write the units in here. But remember, if you don't put this in meters, you're not going to get the right answer. So you got to, even if you use it in centimeters to measure it, you still have to convert it to meters to do the calculation. It asks you for the best estimate of 1/2 g. That's what you're getting every time when you divide h by t squared. You're getting the equivalent of 1/2 g, which is supposed to be 4.95. Okay, you're probably only going to get 3 sig figs, so you compare it to 4.95. If you're getting 4 sig figs, you compare it to 4.950. But in this case, we're probably going to do 3 sig figs. So the best estimate will be the average of these 5. The percent error would be you comparing it to 9.8, or excuse me, to 4.95. That's going to give it here. You don't have to, for this one, show work. You don't have to show work for the average, but you do have to show work of dividing h by t squared. Okay. And you also have to show work either up here for the percent error, or you have to show work for the percent error here. In this particular case, because they said show work, they're actually expecting you to show work for both percent errors. So I would defer to that because they gave you those instructions. So you do have to, in this case, show the percent error calculation twice, but you don't have to show the average, the calculation of an average twice. 10 oscillations of the spring. That's supposed to be another part of the lab. I missed the Oh, there it is. I completely missed this. This was the procedure you're supposed to do. It's to suspend a conical spring, large end at the top, so that it hangs vertically. Attach a 200-gram mass to the lower end. Displace it downward 2 or 3 centimeters, and then release it. It'll go up and down. What you're wanting to do is record the time where it starts at, let's say, the very bottom of its motion, and then say 1, 2, 3, 4, and then when you get to 10, stop the stopwatch, record that time. That's the time for 10 periods of oscillation. And by doing it that way, you've gotten rid of the effectiveness non-quality of your reaction time because you've spread the reaction time over 10 oscillations instead of one. So all you have to do is take that time for 10 oscillations, divide it by 10, and that'll give you the time for one oscillation rather precisely. It's usually going to be on the order of 2 or 3 sig figs, usually a number of seconds with a couple digits for hundredths of a second. You determine that, and then your data, of course, goes right here because you're going to do it 5 times. Here's for the first one, here's for the second one, here's for the third one, here's for the fourth one, here's for the fifth one. Then you have to calculate an average. Again, you don't have to show that work for that average because you've already shown a average calculation, but you're going to put the best estimate for the 10 oscillations here. So these are all the 10 oscillation numbers. You're going to add those up, divide it by 10, and put the answer here. And then you're going to take that best estimate of 10 oscillations, divide that by 10, and that's going to give you the best estimate for one oscillation. Notice it doesn't say any show work here, but you did do a calculation of taking this average number and dividing it by 10. So you should show your calculation of that average divided by 10. Not the calculation of the average, just the average divided by 10. And then finally, the mass of the first pair of masses, the mass of the second pair of masses in grams, and then you're going to calculate a percent difference. In this case, you're actually required to calculate a percent difference and show your work for the percent difference, but that's the only calculation you need. Now, that's the whole document. That's what you're supposed to do, but now I got to show you what the addendum says, and we'll be done with everything I need to explain to you here. What the addendum says for this particular lab is right here. Zoom in again. So it says for estimating pi, you will pick 5 different cylinders, blah, blah, blah. Notice that we've taken a photograph of a part of a meter stick and we've put it on this piece of paper. You can take this to school and print it, or you can just print it at home, and then you can use that as a measuring device. It will be the proper size. And even if it wasn't, it wouldn't matter because you're consistently making exactly the same precision error, so it'll be internally consistent. You might actually take this piece of paper and then cut right along this edge so that you can use it like you want, but it's also a piece of paper so you can wrap it around things and stuff like that. Now, remember, these individual markings are tenths of a centimeter. So when you're reading this, this is the 1 centimeter mark, this is the 2 centimeter mark. This corresponds to 1.1, this corresponds to 1.2, 1.3, 1.4. Notice this tall one always corresponds to the halfway point. So this would be 1.5, 1.6, 1.7, 1.8, 1.9, 2.0. But notice if the measurement is right to the end of my arrow that you see there, then I'd be compelled to call that 1.1, or excuse me, 1.01. So that's how you get a second decimal place in centimeters. If it was all the way down here, I'd be compelled to call it 1.09. Similarly, if it was right here, I would maybe call it 1.11. If it was right here, which looks almost in the dead center of that little black line, then I'd call that 1.10. Notice I have to put that 0 there because that means something in a lab. 1.10 and 1.1 mean nothing different to a calculator, but in a lab, 1.1 means it's a lot cheaper than 1.10, and therefore it takes a lot more work to get the 1.10, so you don't want to ever leave off that second decimal place. So again, 1.10, maybe 1.11, 1.12, 1.13, 1.15, 1.1. I'm guessing that you probably can't tell the difference between 1.12 and 1.13, but you probably definitely can tell the difference between 1.1 and 1.5 and between 1.5 and 1.9. That being said, the difference between 1.1 and 1.11 and 1.15 is 0.04, And we normally state our errors as plus or minus. So if I divide that 0.04 by 2, then I'm getting an uncertainty of 0.02. And that's very reasonable for a meter stick that's marked to the nearest millimeter, is to have an error of plus or minus zero point zero 0.02. If you really work hard at it, you might be able to reduce that to zero point zero 0.01, but I doubt it. Okay. When we use a vernier caliper, we can actually get it definitely to two decimal places, and we should be able to estimate a third decimal place. In the case of finding G, you would drop a golf ball from 78.7 inches or 6 feet, 6.7 inches. They've actually taken the time to convert it to inches because chances are you have some kind of ruler, or you can go to a Home Depot and use a ruler like this. And if you do, they're probably not going to have one in centimeters at your local Lowe's or Home Depot or Taylor Do-It Center. But they probably will, at least the times I've been there and the times students have come to me when I used to work at Home Depot. I was always helpful with letting them, use tape measure to set up something, maybe use a little bit of a pencil or something to mark off a spot, and then drop the ball and time it, so on and so forth. So that's what you're doing there. This lab has a short video of an oscillating spring. Use your stopwatch to time 10 oscillations. And since you don't have a digital mass balance, you can use the following data. Notice these are literally the data that I gathered one time to make this addendum. Actually, I think it was Dr. Wright did this one. But he got 199.77 grams for two 100 gram plates. And then for two other 100 gram plates, he got 199.60. So that's how you do this lab. That entails everything. You're completely free to go. That's, of course, you're always free to go. You don't even have to be here. But that's all I had to do for this lab. Now, normally I would have been done by 10:30. That's why I told everybody, if you want to come here for office hours, show up at like 10:30 and then I can ask questions. But I'm here now for anybody that might have questions, or you can just split. Doesn't matter at all. Julianne and Christopher, do y'all have any questions, or did I say anything that you didn't understand? I know I covered a lot more material than you might have been ready for, and I probably went quite a bit longer than you expected, but now's your chance to ask questions if you have any.
Uh, no, it was a pretty good explanation. A lot was learned. My question would just have to be, is there anything that was missed from yesterday in lecture? Because the site was down yesterday and I couldn't get into the class
Uh, yeah,
or into the Zoom.
you missed quite a bit, but the good news is I record it. So, and it's now on my YouTube channel right now. I put it up this morning. I couldn't put it up last night because it took too long to download, but I did put it up this morning around 6:30 or so. So you can find it there. My YouTube channel, of course, is actually, let me type it up here. That's the easiest way. My YouTube channel is www.youtube.com/ at symbol. See that physicsolutions.com with the capital P, capital S, capital D as in dog, and capital C.
Oh,
That
yes.
is it. So if you go there, you'll see. Now, you don't necessarily see it right now because these are the more popular ones, but if I look at the video list right here, you'll see this is the one I did last night, unit and dimensional analysis and Fermi calculations. This is what I did in 242 the day before, and this is what I did the first day of class for you guys. So that's our first day of class. Something that's really important, and I explained this in lecture before, but you might not have got it. Let me do it now. When you click on this right here is that little code I've been warning people about. And you'll see that's there on all of my videos, except for ones that are just standing alone videos instead of lectures. And the code that I'm talking about is the 01142026. What this means is this was my PHY 241 class, specifically my N02B section on January 14th, 2026. But if you go reading or watching this video and you can't read my notes because became pixelated because of bad internet connection or something like that, or because you're
Mm.
watching it on an itty bitty screen, then all you have to do is go to my Google Docs, which you have a link to in my helpful documents and links, and do a search for that 01142026, and boom, that'll be the notes. Because I take notes in my iPad and then I upload them to my YouTube channel, I mean, to my Google Docs immediately afterwards.
Okay. All right.
Okay.
Thank you.
You're welcome. Sorry for answering your question with so many paragraphs. I write the same way on my Facebook page, so people hate me. How about you, Julianne? Do you have any questions?
No, I'm okay.
Okay.
For right now. Thank you though. I appreciate it.
No problem. And you guys can always come here. I did say that I can change this time. So if I actually, if you know a bunch of people in your class and several of them wanted at a different time, if someone asked me to do this at a different time, if it fits in my schedule, I will consider it. But what I'm going to do to decide is send an email out to everyone and say, hey, 10 o'clock on Thursday, how many of you could make that? Okay. How about this other time that the class is asking? How many people can meet that? If more people can meet in that other time, then I'm going to choose that other time. But generally speaking, unless somebody comes to me with an alternative time, I'm just going to keep it at this 10 a.m. every Thursday. All right. Well, thank you for coming, everybody. And since you don't have any questions, you're free to go. I'm going to go ahead and stop sharing my screen and call it a day. And I will post this on my YouTube channel soon. Hopefully, I did not just record that with your picture up the whole time. That might have happened. Hmm. I wonder if that happened. Oh well, we'll see. But have a good one, everybody. Take care.
All right. Thank you.
Bye bye.
Thank you, you too.